Okay, so today I'll discuss our new work on the rate of convergence in the stable domain of attraction in the Wasserstein metric. This is joint work with my two former PhD students, Jorge Gonz, azares, who is at UNAM in Mexico City, and David Bang, who is at Aarhus in Denmark. Okay, so classical situation, I have a CLT of this type, where M is Gaussian if the increments of the walk have unit variance and zero mean. Okay, so I get this sort of converges. This is well known. The same thing happens for the Levy process. Okay? I scale a Levy process that has a second moment, square root t, as t goes to infinity, it converges weakly to M. Now, because M is nice, both Kolmogorov distance and Wasserstein distance between this approximation and the limit M tend to zero as t goes to infinity. And the question is how fast, and of course that's an important question in applied probability, and there are many important answers to it. In particular, for example, there is the Berry-Seen that says that if the increments of the walk have 2 plus epsilon moments, then the rate, upper bound on the rate of the Kolmogorov distance is 1 over square root of n, and the same holds for the Wasserstein distance. Okay. Today, my interest is in the stable domain of attraction, so I'm converging to a stable law. I want to look at the multidimensional Levy setting, and I'm interested in the small time regime. So this is the overview of my presentation. I'll discuss the setting, I'll tell you about the results, the rates, and then discuss the couplings that yield upper bounds, 2 couplings. Okay. So what's the setting? I take an arbitrary Levy process in RD that is attracted to an alpha stable Levy process in RD, which is an attractor. It's unstable. It's a Levy process that has self-similar property, and alpha is the stability index between 0 and 2. Now, X is in the domain of attraction of Z if this scaled version of X, scaled by this function g of t, converges weakly to Z on the interval, say, 0, 1. So g is a function that goes to 0, okay, goes to 0 polynomially at the rate of 1 over alpha, and is multiplied by this capital G, which is a slowly varying function at infinite. Okay, so here you see I'm sort of blowing up the process and looking at it at shorter and shorter time intervals. Now, this capital G is hugely important for the rate of convergence, as you will see. And there's 2 possibilities. We say that X is in the normal domain of attraction, that this capital G has a positive finite limit. And it's in the non-normal domain of attraction if this is not the case. Okay, now the question is, what's the rate of convergence, right? This is the scale X. How fast does this converge in the Wasserstein distance? Right, quick reminder, Wasserstein metric for 2 processes, I take them, they're coupled, I look at their difference, look at the supreme norm to power Q, expectation, take the infimum of that. Important here for me is that I allow Q to be smaller than 1 because my limit, certainly Z, doesn't have second moment and sometimes not even the first moment. Okay. Of course, marginally, if I take just a vector in RD, the Wasserstein distance between the laws of this vector is defined in this way. Similarly works for any Q, but what I want to draw your attention to is that from these definitions it's evident that the marginal distance lower bounds the distance in between the processes, and this we'll use when we sort of try to understand this question. See, I'm interested in these 2 question marks today, right? As t goes to 0. That's my point. Now, classical Berry-Seen approach cannot work because Z doesn't have the second moment. Okay, so there you need 2 plus epsilon because you need some uniform integrability to work, and uniform integrability is genuinely a problem in this context. Q will be varying between 0 and alpha because the limit doesn't have moments alpha and above. We're interested in the Wasserstein distance, and Emmanuel Rio in 2009 had this nice paper where the upper bound on the Berry-Seen situation for the Wasserstein distance in the Gaussian case is obtained, and that relies on the Komron-Schmeijer-Tisnadi coupling between Brownian motion and pure jump Levy process. Okay. Now, in our case, we need to couple the processes directly. This is not, comparison with Brownian motion is not a good idea. And we want to have asymptotically matching upper, so we get an upper bound and we need to prove that this upper bound is good, right? The coupling is good, so the asymptotically optimal. Right. So you will see this is different in the normal and non-normal case. In the normal case, we use Kantorovich duality and the Toscani-Fourier lower bound method. And in the non-normal case, we generalize the approach of Burgers and Greenberg for Prokhorov distance. It was in their case. Now, this slide just tells you why this understanding the rate of convergence to zero of this quantity is relevant, but I will just skip it and get on with the result. Okay. Now, what's the setting, right? So I have this scaled Levy process. Remember, G is slowly varying, Z is alpha stable, and I take alpha between 0 and 2, and I take some Q, which is smaller than alpha in not greater than 1. And here are our results. So in the normal case, in other words, when this G has a finite positive limit, then the easiest way to understand this is to think of alpha between 1 and 2, and then Q equal to 1, right? If Q is equal to 1, and alpha is between 1 and 2, then the upper bound is T to the 1 minus 1 over alpha, and the lower bound likewise. So this quantity, W1, L1 Wasserstein distance, converges to 0 polynomially, because when alpha is greater than 1 is 1 minus 1 over alpha, of course, positive, so this converges to 0 polynomially. In the non-normal case, the situation is drastically different. So for Q is 1, this Wasserstein distance will, the maximum of the two, will be of some slowly varying order, and this function L is given by this. Okay, so here I'm only assuming that G is differentiable in order to write this down. Our general result is more general than this, but if it is differentiable, then this kind of thing will hold. Okay, so this L has an interesting feature, that it cannot be dominated by a non-increasing, by an increasing integrable function L, which is integrable with respect to this measure that preserves scalings. Okay, so if such a function exists for any such function, then my bound dominates this L. Okay? In other words, for example, if I take L of t is 1 over log t to the power 1 plus epsilon, that's definitely integrable. Because this property holds, it means that along some sequence that goes to infinity, this lower bound here is going to be slower than logarithmic for any epsilon. So that's the first thing. You see, there's a big difference. Here it's polynomial, and here it's never going to be faster than logarithmic, at least along some subsequence. Now, yes, one should compare normal and normal. Now, let me just try to say a few more words about why this non-normality leads to such slow convergence. So we have this situation. We are in non-normal case, so this means this G does not have a limit at infinity, finite positive limit at infinity. So how do we establish our stuff, right? So we prove this fact 1, which is again sort of inspired by results in Berger and Greenberg that I mentioned earlier. And this is, you see, the lower bound is essentially given by this difference of 1 and this quotient of G at 2t and t. Okay. So here this proof really relies on the fact that I have to look at these two Wasserstein distances concurrently. Okay, of course, conjecturally, such an inequality of this type should hold for either of them, but this is something we don't know how to prove. But in any case, we know how to prove this, right? So this is for all small t will hold. And then the second point has nothing to do with Levy processes, but was also extension of this Burgers and Greenberg paper, where it's to do only with slowly varying functions. You see, if I take a slowly varying function L, arbitrary slowly varying function L, take some constant lambda which is not 1, and then build this kind of expression which is analogous exactly like this expression. And then if I can bound this expression by a function that is decreasing and makes this integral finite, then that tells me that this L must have a positive finite limit. In other words, if I'm in the non-normal domain of attraction, such phi lambda cannot exist. And this has nothing to do with Levy processes. As I said, this is just an argument to do with slowly varying functions. Now, from this, immediately it follows the stuff that I had on the previous slide. I have this lower bound along some subsequence. Right? But you see, somehow also, curiously, this G, I can take, if I take a very, very slowly growing G, I take, for example, 100 logarithms right? So this G is slowly growing. It's like a composition of 100 logarithms. So in other words, in this process, this G, this is nearly constant. Okay? This is nevertheless still in the non-normal domain of attraction. In that case, we can analyze this lower bound and prove that it actually holds that this lower bound is always greater for any epsilon than 1 over log 1 over t, 1 plus to the power 1 plus epsilon, for all t, not just along some subsequence. Okay? So in other words, for such Levy processes, I have this scaling function, puts it in a non-normal domain of attraction, but this cannot be detected. This is not different from a constant. Very far, you have to go to see this is different from a constant. And so statistically, from the trajectory of the process, is sort of undetectable. And yet, the rate of convergence is logarithmic, not faster than logarithmic, while if it was actually a constant, rate of convergence would be polynomial. Okay, another perhaps interesting fact is that if I take a slowly varying function, arbitrary slowly varying function, that goes to 0 at infinity, and that of course makes this integral infinite, then there exists a Levy process that converges this slowly to 0 in the distance, the Wasserstein distance between xt and z converges to 0 at that given rate, and the prescribed rate. And finally, another thing that comes out of this analysis is that if you fix a process and you take two different slowly varying functions that are asymptotically equivalent, the rates may be vastly different. So the rates, this one is much smaller than this one sometimes, and this one is much larger than this one sometimes because of this. Okay? So you can change the rate of convergence by changing. You see, the fact that you're in a domain of attraction really just tells you that such a G exists, and this G is determined only asymptotically. But if you change how you approach this asymptote, you can change significantly the rate of convergence of this process to its attractor. Okay, so that's about lower bounds. Now, to talk about upper bounds, I need to discuss some couplings, and I need some very mild but still nevertheless structural assumptions, because the lower bounds were completely general. So we have two couplings. The first one that I'm going to discuss is thinning coupling, and we need to essentially couple the Poisson point processes of jumps of the two Levy processes. And here is the description. So these are the small jumps, these are the large jumps of X, integrated against the compensated Poisson point process, Poisson random measure, or just the random measure in the case of the large jumps. Now we're going to couple the measures, the Poisson point processes. So how do we do that? Thinning coupling does, I take my Levy measures of the processes and I take a dominating measure, this mu, for example, the sum of these two measures. And then I look at these two densities, right? We take inspiration and simulation. Now, what we do is I take this measure mu and I generate a Poisson point process driven by mu, and then decorated with these uniforms, and I take additional uniforms that are independent of this xi, capital Xi, and then I just thin. Right? I evaluate the density at the jump, and if it comes greater than this uniform, then I take it, and if not, I don't, and I do the same thing at both sides. Right? And mapping theorem for Poisson point processes tells me that these two Poisson point processes are indeed Poisson point processes. It corresponds to the jumps of X and Y respectively. Okay, so here's a simulation of that. Right? You see, here is the jump. This is 0 somewhere here. The jump is here that I took both. This is a jump where I only took one. This is a jump where I took both. You see, so I try to sort of match. I try to match jumps with largest possible probability. That's the idea. And then once you have this coupling, you have the measures are coupled. You can put them in the same probability space, and you can obtain an upper bound of this type. And as you saw, this is used in the normal domain of attraction. This is in fact asymptotically optimal. Now, in the non-normal domain of attraction, we use a slightly more sophisticated coupling, which we term comonotonic coupling of X and Y, which is based on this Lapage representation of the Levy measure of a Levy process in terms of the sort of decomposition with respect to the radial decomposition. Right? So I take the Levy measure, okay, mu x, and I write it as a probability measure on the sphere, the minus one dimensional sphere, multiplied with the mass on the sort of density function or distribution function on the ray. Okay, I do that for both of these two guys. And then I create a new probability measure in the sphere by just taking the average of these two. And I look at the densities, mu x with respect to mu, and sigma y with respect to sigma. And now you see, I can write mu x integrated with respect to sigma, not sigma x anymore, but the sigma is the same now in both cases, except that I need to sort of change this multiplicative factor. And the multiplicative factor here is this density is just multiplied, so on each ray I just multiply by constant on that ray, obviously, and the constant depends on the density that I've introduced. Fine. Now, so these couples, you see, this sort of aligns the angular component of each jump. And now what am I going to do with masses on the rays? Well, I'm going to use the best possible coupling that I can, which is the comonotonic coupling for the masses. And the comonotonic coupling, you see, is given by this sort of inverse CDF, right? You see. So this guy is the inverse of the distribution function on the ray. Right. And then, so Jan Rosinsky has this very nice paper where he discusses these series representations, including this Lepage's series representation for these things, and it's sort of given in terms of the following ingredients. So gamma n's, this is just the jump times of a Poisson process, which I then decorate with the UN. I mark it with independent UNs, and which I can also then mark additionally with the jumps, sort of angles of each jump, coming from this measure sigma, and this gives me a Poisson point process of this type that I can then really also Poisson random measure, which I can also compensate. And then I can express both of my processes in terms of this, right? So here, this is the small jump processes, you see. We start with the jumps of the Poisson process, right? So you see here, small jumps correspond to the remainder of the times the Poisson process jumps, right? So infinity, right, in this component. And for the big jumps, I need to look at really the first few, because we're looking here. Remember, we're looking at the interval 0, 1, right? So t runs from between 0 and 1, and these are the big jumps. That's how this representation of Rosinsky works. Okay. Now I get these representations here, and now everything is nicely coupled. And you see here, this is a picture that tells me how this thing actually works. So the angles are aligned always, and the masses are coupled optimally, right? Optimally in the sense that I take this comonotonic coupling, which is known to be optimal in the one-dimensional case for the LP Wasserstein. So, and this then produces an upper bound, you can prove, of this type, once they're coupled like that, and that produces this sort of optimal coupling for the asymptotically optimal upper bound, which matches the lower bound. Okay, so these are the papers that I mentioned in this presentation. Thank you very much for your attention. Paper is available on arXiv if you're interested in this sort of thing.